Hello and welcome to ECMath. Today we're going to look at the graphs of polynomial functions. There is a companion worksheet that goes along with this. I'll try to link it in show notes, and if you're in my class, I will have linked it in your classroom as well. But go ahead and take a minute now and print that thing out so you can follow along. So first, let's just do a little review of what the term polynomial means. We'll start with some examples. So here are some polynomials. X to the fifth plus 3x squared minus 2x plus 1, that is a polynomial. So is negative x to the fourth minus 3. So is 7x to the 10th, that's a polynomial. As is, by the way, 2 is a polynomial. These are all examples of polynomial. Key features are that they have whole number, that is positive integer exponents, 5, 2, 0, and coefficients can be any real number. No imaginary coefficients, but any sort of real number is allowed. The general definition of a polynomial is a little bit mathy, but it goes like this, and it's, I think, important to work through a definition like this. an x to the n, that's the first term, plus the next term we call an minus 1 x to the n minus 1. So the an's and n minus 1's are the coefficients, the x is the variable x, and the n's are the n's and n's minus 1's themselves are the exponents. The pieces with the a, those are just subscripts that say that this a goes with that x. Then you sort of get the pattern. We're descending power, and we skip a couple terms. Then at some point we come to a2x squared plus a1x to the first. And then at the end, you might have what we call a constant term, a naught, which is just some, real number at the end. And we usually say that that's a function, so I'll call this p of x, the polynomial, is equal to that. And that's just the generalized term. And then to recap again, the an's, those are the coefficients, can be any real number, but the exponents need to be whole numbers. Or I guess 0, depending on if you decide the whole numbers include 0 or not. But that's our general definition of a polynomial. Then key term for a polynomial is degree. Degree is the n value. That is the highest exponent when it is all multiplied out. And I add that clause of when it's all multiplied out because sometimes you get polynomials in factored form. It's not just the highest exponent of a single factor, it's the highest total exponent. We'll do an example and look at that in a second. We also say that the leading coefficient is that a sub n value, and that is, of course, the coefficient of the highest exponent term when it's all multiplied out. And importantly, like the most important thing about an is deciding, is this positive or negative? That's going to really affect the shape of the graph, whether that's opening up or down. Let's flip to the back of this sheet. The very back, very bottom of the sheet, if you printed it out, there's example 4. Negative x cubed minus 2x squared plus 4x plus 8. That is a polynomial. And let's just for now write the degree and leading coefficient. So the degree is the highest exponent. That's 3. So the degree of this is 3. And the leading coefficient is whatever's multiplied to that term with an x cubed. And in this case, it's negative. So that's going to be negative 1. So the leading coefficient is negative 1. And really importantly, it's negative 1. Let's do another one. Let's go and jump up. We'll skip examples 2 and 3 for now, but go back to example 1, because that comes to you in factored form. So you might, let's do the leading coefficient first, actually. That's easiest. We can see that the leading coefficient is 2. And we would need to check maybe that there wasn't some other like, a 3x minus 1 here, because then the real leading coefficient would actually be 6. There's not. So the leading coefficient is just 2, and every other coefficient on x is 1, 1, and 1. But what's the degree? You might be tempted to say that the degree is 3 because of that x third, but it is not. Degree is the power of x if you did multiply this out. And you don't have to multiply this out, but imagine that if you did, you would end up doing 2x cubed times at some point you'd have to multiply it by that x, and at some point then you'd have to multiply that result by that x. So you'd end up at some point with a 2x to the 5th term, which means that your degree is going to be 5. Then there's going to be, of course, a bunch of other terms in here to actually do the multiplication. It's not just 2x to the 5th, but when we're just finding degree and leading coefficient, you can kind of think about it as if it was only the leading terms multiplying in together. All right, so those are some key facts about polynomials. What about some facts about their graphs? What do their graphs look like? Well, the reason we work with polynomials is that their graphs are always predictable, and they pretty much have the same graph with some small differences. So here's what all polynomial graphs will have in common. If you zoom in a little bit, they have smooth rounded corners, no sharp edges, smooth rounded corners around their minima and maxima. They often have zeros or x-intercepts, but they don't have to. And they have no breaks, no jumps. And as x goes to infinity, they usually go up or down. And you can see on this one, as x goes to infinity, the graph is trending upwards. As x goes to negative infinity, the graph trends downwards. On the other hand, on the right, you can see some graphs that are not polynomials. Your graphs of polynomials should never look like this. They should never have any kind of breaks, and they should never have any kind of sharp corners. If you find yourself making a graph with any of those features, it is not a polynomial graph. Smooth curves, zeros and intercepts, nice, well-behaved end behavior to the left and right, no breaks, and no vertical or horizontal asymptotes, which you may not know what those are yet, but they don't have them. I mentioned a second ago end behavior, and that's what we're going to go to now. So go ahead and flip back to the first page of your worksheet, and let's fill in the leading coefficient test for end behavior. When we decide the end behavior of a polynomial, which is what happens to the far left and far right of that graph, what matters are the degree and the leading coefficient. Those are the only two things that you need to look at. The rest of it for this test doesn't matter. It matters for other parts, but for this test, it doesn't matter. By the way, at the end of the video, I'm going to talk about why this test works, but I'm trying to front load all of the mechanics so that you can fill out your sheet and have a good solid batch of notes, and then so you can stick around for the end to understand all of the why these mechanics work. So for now, let's just do the first piece of the leading coefficient test. And that's going to be if the degree is even and the leading coefficient is positive. So I'm going to write a plus, but I'm going to maybe make a note that that means positive. The graph will, and I'm just going to draw a picture or a sketch first. The graph will generally, as x goes up, so that's x, as x goes to the right, the graph will trend upwards. And as x goes to the left, the graph will also trend upwards. Now, in the middle, there could be all kinds of other stuff, right? The graph could go up and down and woozy-woozy. This is a sharp corner. I'll just try to eliminate that sharp corner a little bit. But the graph could go up and down all around in the middle. That doesn't matter. This is all about what happens as x is either very big or very small. And if the degree is even and the leading coefficient is positive, the graph will go up and up. A shorthand that your book likes to use is they just draw two little arrows, kind of like this, to say that's the end behavior. That's not very formal. So formally in math, actually kind of semi-formally, there's even fancier notation. I'm going to say this. As x approaches infinity, so that arrow is read as saying approaches. F of x, that is the y values, approaches infinity. So let's decode that. That's basically saying as x approaches infinity on the x-axis, so that's over here, f of x, which is really the y, approaches infinity on the y-axis, or goes up. You can't reach infinity. We can't say, oh, f of infinity equals infinity. That would be completely ridiculous. So we have to do this kind of strange notation to say, well, we can't actually plug in infinity, but if you could, the output would also be positive infinity. It would be going up. We can also talk about going the other direction. So we could say as x approaches negative infinity. So that's starting at 0 and traveling to the left towards negative infinity on the x-axis. What does y do? Well, in this case, f of x, aka y, is also approaching infinity. This is the notation that if you're going to write end behavior, I'd like you to start using. It's kind of a mix between this least formal behavior notation and something more formal called limit notation, which we might teach you later in class. But for now, stick with this arrow stuff that really kind of talks about what's going on. I think we're going to go out of order here and go straight down to box 6. In box 6, we're going to talk about if the degree is even and the leading coefficient is negative. This is basically a reflection of the behavior when the degree is even and positive. So what will happen in this case? Remember the other graph which went up and up? In this case, if your degree is even, your leading coefficient is negative, your graph might do something in the middle, right? And there might be all kinds of nonsense in the middle, but you know that at the ends, left and right, the graph is going to trend down and down. Informally, we could write, down, down. This is like what you'd write in your notes, maybe. But if you were being a little more formal and you wanted to describe the end behavior, you would say, as x approaches infinity, f of x approaches negative infinity. So that's the infinity on the x. And this is the f of x approaches negative infinity on the y. And as x is approaching negative infinity to the left, which we'd write like this, f of x is going in the same direction like that. So that's our even negative behavior. It's basically a reflection over the x-axis of the even positive behavior. Let's go to box 5 and talk about odd positive behavior. So odd polynomials, odd degree with positive leading coefficient. So what will these look like? Well, in this case, the graph, think about having a negative number and taking an odd power of it, like negative 50 to the 7th. I don't know what that's going to be, but I know that it's going to be a negative number. That is, to the left, the graph needs to go down. So there might be some kind of garbage going on in the middle, stuff in the middle. But on the left side, because I have negative numbers and I'm taking higher powers of them, they will stay negative and just get bigger and bigger. But on the right, if I have positive numbers and I take higher and higher powers of positive numbers, they're still going to go positive. So an odd degree polynomial might have other stuff going on in the middle, but to the left and right ends are going to be one up, one down. So this one we might write, informally using this kind of notation, and more formally, I would say, as x approaches infinity, f of x also approaches infinity, but as x approaches negative infinity, f of x approaches also negative infinity. So this is and remember, just looking on the graph, that's the x, as x approaches infinity on the x-axis. This is the f of x approaching infinity on the right, but on the left, we have x approaching negative infinity. We have f of x approaching negative infinity. That's basically the fancy way of saying goes down. And let's do the last one, which is an odd degree, but a negative leading coefficient. Just like the last one, this is going to be a reflection of the one we just did. We'll draw that out. As before, there might be some kind of garbage going on in the middle. Who knows what this is? But in the end, the right side, you have a negative leading coefficient, but positive powers of positive numbers, so the total is going to be going downwards. On the other side, you have positive powers of negative numbers with a negative coefficient, and the negatives kind of cancel out, and the graph is going to be going upwards as x goes far to the left side. So we would write this maybe as like up, down, and more formally, I would say as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, so the left side, f of x approaches positive infinity. You have that kind of flip-flop of the signs. Just as a summary, here's everything that we wrote in one box. So we can pause and write that down. Oh, by the way, sometimes this is confusing with the notation. Remember when we were doing increasing and decreasing functions, we always read from left to right? For these, when we're talking about approaching positive and negative infinity, we are reading from the center out. That really matters on the negative side. Sometimes folks will say, oh, but it's approaching 0 because they're reading from left to right. When we talk about end behavior, we're reading from the center and working out. All right, so that's the end behavior test, and we can use that, of course, to figure out what's going on at the ends of our graphs. But now we need to talk about what's going on in the middles of our graphs, where I have those dotted lines, and that's going to be the next segment of the sheet. Once you've determined the end behavior of a polynomial, you've basically learned all you can from its full polynomial form. And the next step before you go any further is just to completely factor that polynomial. That's what we need to do to learn more. Now, factoring is outside of the scope of this video. There's so many factoring techniques, and we've seen some of them before, and some of them just need to be practiced, so we will do some examples later, but I'm not going to talk a long time about factoring. Let's just assume that you have had some gross 5th degree, 6th degree polynomial, and you factored it completely, and you maybe got a result that looks something like this. We'll just do example. Maybe you got x minus 1 times x minus 1 times x plus 2, x plus 2, x plus 2, this is really terrible, times x minus 4 times 4. Wow, that's a heck of a polynomial. That must have been a terrible pain to factor, but we'll pretend that you had a good time with it. One thing that you can do, of course, is condense this a little bit and write this as 4 x minus 1 squared x plus 2 to the third x minus 4. And these are all multiplied together still. And this is a really important step because in this form, it reveals something about each factor, and that what it reveals is called the multiplicity. So what is the multiplicity of a 0? By the way, I'm going to use the word 0 and factor interchangeably here because I recognize that if I have a factor of x minus 1, that means I have a 0 at x equals 1. Those are the same idea. So zeros and factors are really the same thing. I think that's called the factor theorem. We've talked about it before. But the multiplicity of a 0, back to this. What is it? It is the number of times its factor occurs in the fully factored form. You can also think about it as the exponent on the factor. So, for example, in my example polynomial here, we have an x minus 4 has an exponent of 1. So that's a 0, right? X minus 4, which has a 0 of x equals 4, has a multiplicity of 1. let's go through and actually kind of chart this out. So that's our multiplicity 1. We have x plus 2 to the third, which gives you a 0 of x equals negative 2. That's the 0. That has a multiplicity of 3. And the x minus 1 squared gives you a 0 of x equals 1. That has a multiplicity of 2. And the graphs will behave differently at each of these kinds of zeros. The graph will touch the axis at every 0 here, but what it does and how it behaves is slightly different. So that's what I want to talk about. At a 0 of multiplicity 1, the graph of a polynomial will cross through the x-axis. And it will do exactly like this. So if this was our graph, let's say, so we should have a 0 at 4. I'm going to add a couple more other zeros of multiplicity 1. Let's say these are all zeros of multiplicity 1. Then the graph would go straight through. It would have to turn around between the zeros, cross through again. It would have to turn around again, and cross right through. And notice it crosses through, and if you were to zoom in on that crossing, it would just look like a straight line. It's just going right through. That's probably the type of zero you're most used to. When a parabola crosses through the axis, that's what it does. When x cubed, actually x cubed is different. When a parabola crosses through the axis, that's what it does. Odd multiplicity zeros, so specifically multiplicity 1, odd multiplicity zeros not equal to 1, so 3, 5, 7, 9, I'll just say odd, but not 1, are going to have a slightly different behavior. They're going to cross through the x-axis. Oh. But they're going to flatten out 2 t's as they cross. They're going to cross through and flatten out. We'll say cross through. Here's what that looks like. So in this example, we said that there's a 0 at negative 2, so I'll mark that one. And let's say there's also another multiplicity 0 at 5 or something in this example polynomial. So it would be sort of maybe coming up from the bottom. It could come up from the top, but just in this example, it's going to come up from the bottom, cross through, but as it crosses, it kind of does a little wiggle, turns back up, begins increasing again, and then it's going to have to turn around, come in, get closer and closer to that 5, closer and closer to that 5, and as it approaches the 5, it's also going to kind of flatten out like this. And so sometimes we call it a wiggle. It's just sort of this flattening, and that has to do with the fact that as you go near that 0, you have a higher exponent, so it's not just going to go straight through. There's going to be some kind of weird behavior with the wiggling. But it does change the shape, because if I didn't draw that flattening, I could just draw basically a parabola that hit those 2 zeros. But those 2 graphs are not the same. So I think it's really nice to try to show that flattening in there. Technically, the higher the multiplicity, like a 5 will be slightly flatter than a 3. A 9 will be really, really flat. That is, in a graph sketch, probably not worth trying to show. But showing the little bit of flattening, a little bit of wiggle, I think that's pretty cool to show in a graph. All right. What about a 0 of multiplicity 2, 4, 6, or 8? So those are zeros of multiplicity that are even. Well, a 0 of an even multiplicity is not going to cross the x-axis at all. In this case, the graph will touch the x-axis and then turn around. Sometimes we call this a bounce. So here is an example of a 0 with that kind of multiplicity. We're going to come in, so maybe here's we said it was 0 is at x equals 1, so here's x equals 1. we might come in from the top. You might have some other kind of piece of graph doing something else over here. And we're going to come in from the top, touch that axis, and just turn right around. And kind of like a parabola, like x squared, right? It's just going to touch the axis and turn around. If you had a different zero, maybe a different graph, you can also touch the axis and turn around from below. So you could come in, something like this. The graph is coming in, touches the axis, turns around, and then goes off and does the rest of its graphiness. So even multiplicity zeros, the graph will touch and bounce. And here again is that whole chart all in one. So depending on the multiplicity of the zero, which is the number of times that factor occurs in the fully factored form, you could have three potential behaviors. The graph might cross right through at that zero. The graph could cross through and flatten out at that zero, or the graph could touch and then turn around. And that's it. So we've completed the whole first page, and just to give you a big picture, these two tests for end behavior and then zero behavior are going to tell you everything you need to know to graph a polynomial. It's pretty cool, actually, that such a complicated graph can be determined by 7 little tests. That's pretty impressive to me. I know it feels like it might be a lot, but that's not a lot of things to determine like a very complicated behavior. So we're now going to flip to the back and look at some of these examples. All right, let's start with example 1. We already did the degree and leading coefficient of example 1. The degree was 5 and the leading coefficient was 2. And in this case, now that we know the leading coefficient test, I'll make a highlight that that's positive 2. We can fill in the end behavior then. So that's odd, degree, and a positive leading coefficient. So the end behavior informally is going to be odd positive behavior. It's going to look like that, which we can say as x approaches infinity, f of x will also approach infinity. As x approaches negative infinity on the left side, f of x will approach negative infinity. Now let's talk about the zeros. I like to approach this with a zero chart. So first, just to zoom in on the function, 2x cubed, x minus 1, x plus 5 is already in fully factored form. There's 3 distinct factors. There's the x cubed, there's the x minus 1, and there's the x plus 5. If you don't believe x cubed is a factor, maybe you should think about it as x minus 0 cubed. If that helps you see it structurally better, fine. These are going to give us then 3 zeros. This will be a 0 when x is 0. This will be 0 when x is 1. And this will be 0 when x is negative 5. Before I even sketch the graph, I like to make a chart of the zeros in order with their multiplicity. So here's what that chart looks like. I write 0. I write the multiplicity. Just do mult for multiplicity. And then I write the behavior. This is just going to help me keep track as I go into the chart. So if I have my first 0 from left to right is negative 5, then I have a 0 at 0, and then I have a 0 at 1. I'm just taking these zeros that I wrote and putting them kind of in increasing order. Then each of those zeros has a certain multiplicity. That's the exponent on the factor. The 0 at 0 had a power of 3, so that's a multiplicity of 3. And the zeros at negative 5 and 1 only had a power of 1, so those are multiplicity 1. The behavior, I'm going to look at the chart from the other side about whether it crosses, bounces, or flattens. And I'm going to say that at multiplicity 1, it's going to cross straight through. And at 3, it's going to cross straight through, but flatten out. So, armed with my end behavior and my zero chart, it is now fairly trivial to actually graph the polynomial. Here we go. By the way, you'll notice on my graph I haven't scaled the y-axis. That's important. We're just sketching the graph. Like, that's all we're doing. So you can label your x-axis. Don't bother labeling your y-axis. We don't know how to find the y values yet. We're just looking at the x. Okay. So first, I'll plot the 0 at negative 5. I'll plot the 0 at 0, and I'll plot the 0 at 1. Oh, I have some zeros really close together. That's fun. Okay, we'll have to zoom in when we plot those two. Let's also, I'm going to sketch in the end behavior to the left and right, just to tell me where I'm like kind of going. Once you've got all that on your graph, all you have to do is kind of connect the dots. It is best to use like a pencil and kind of sketch it in first before you go straight to your pen, just in case there's some weird subtlety. But basically start on the left and work towards the right. I know that the graph needs to be pointing down at the very end, so I'll draw like an arrow there. I'm using my pencil, and I'll go over it in a pen when I'm done, just when I'm to be sure. And then the graph's going to kind of come up this way. It's going to cross right through at 5. It has to turn around because I have to then get to the 0 over at 0. Now, as I approach the 0 at 0, I'm not going to go straight there because I know the graph needs supposed to cross and flatten out at that 0. So I'm going to kind of target artistically a little before that 0, so when I get here, we can flatten the graph out, cross right through. I know this isn't perfect. I'll fix my sketch at the end. Cross, flatten out, go back down, and then you have to turn around real quick because you have to get back to the 0 at 1. So turn right back around, go right up. This one doesn't flatten out. It just goes right through and goes out to the end. Something like that should be your graph. I'm going to erase my pencil marks and clean this up maybe a little bit. Something like that is a perfectly valid sketch of this polynomial. And you may be asking, I know people always do, like, hey, Mr. Eck, how do I know like where to put that peak and valley and the exact value there? The answer is you don't. There is a technique involving calculus that you can use, but we don't know it yet. So you're gonna have to save that question for next year. You will find that out. We just don't know it yet. So for now, just kind of make it look like a nice smooth curve, look like a polynomial, and it's going to be good enough. When I kind of go look at your work, I'm looking for the zeros. I'm looking for the behavior at the zeros, that is, does it bounce, cross, flatten? And I'm looking for your end behavior. Those are the key features that we're looking at and trying to make sure are accurate this year. So that's the procedure for graphing a polynomial. Decide your degree and end behavior, decide your zeros, make a zero chart, and then connect the dots and sketch the graph. If you feel really confident right now, I would encourage you to pause this video, try the remaining examples, and then check through the video and see if you got them right. If you're feeling a little less confident, then just stay watching here and, we'll do them together. Okay, so let's go on and do example 2. So the degree is going to be the sum of all the exponents on x. So here I have an x squared, here I have an x to the first, here I have an x to the first. So that's going to be degree 4. That's because this is in factored form, not polynomial form. This is not, the standard form. So in factored form, you have to look at all the sum of all the exponents. The leading coefficient is going to be the product of all the coefficients of x in that same idea. So I have a -2. This is 1x, 1x, and 1x. So really the leading coefficient appears to be just be -2. So specifically for degree, we have an even degree, but a negative leading coefficient. We'll just circle that, which means that our end behavior is going to be down to the left and down to the right. So formally, I'll write as x approaches infinity, f of x approaches negative infinity, and as x approaches in negative infinity, f of x also approaches negative infinity. That's saying it's going to the left and right, the graph is going down. Let's take a look at the zeros. So let me clear that off. There are 3 zeros again, or 3 factors, so I'm going to have 3 zeros. This is going to be x equals -3. This will be x equals 1, and this will be x equals 4. So those are the 3 zeros. Let's put that in a chart. So we'll say this is the 0, this is the multiplicity, and this is the behavior Let's do BEH for behavior. What does it do? So put them in an increasing order now. I think they're already in increasing order. That was convenient. So 3, negative 3, 1, and 4. The negative 3 had a multiplicity of 2. Then these both had multiplicity of 1. So the multiplicity of 2 is going to bounce off the axis or turn around. Touch and turn around. The multiplicity of 1 zeros are both going to cross. So that's everything in theory that we need. Let's go to the graph. I'll plot the 0 at negative 3. I'll plot the 0 at 1. We'll plot the 0 at 4. I'm going to sketch in my end behavior, which is down and down, just as a reminder. And then I'll take my pencil and just kind of lightly sketch what I think is going to happen. So I have to start down with this arrow, and then I have to connect that to the negative 3 by like bouncing and turning around. Okay, then I have to come around, I'll cross the y-axis, and then I have to come over to 1 and cross the axis. So I'll come over to 1 and cross the axis. And then you have to turn around again, and we have to cross again at 4. So we're going to turn around in a positive direction here. Smooth curve again, cross at 4. And it's going to have to go down like that. Now I had some wiggles here. I'm not very happy with this shape. So let me clear the pencil mark off and clean this up maybe a little bit. But this is what I'm looking at, just sort of thinking through. I can clear these off of here also. Clear that out. And clean this up with my pen. So we're going to go arrow. Nah, that's a bad arrow. Bounce. Cross. Cross. And down. Don't forget to add arrows on both sides. It's just a good habit. And that would be a good graph of your polynomial. I'll highlight my zeros again. That's a pretty fair graph of f of x. Again, we have no idea of knowing where those values are. They're probably not like directly at the midpoint of the zeros, by the way. Like, don't assume that they're right in the middle because the symmetry is all weird with these. So just, again, make a nice smooth curve sketch. So that would be a perfect sketch of this polynomial. Let's go look at example 3. All right, so in example 3, it's now in the standard polynomial form. So we can just look at the degree from the highest exponent term. So that's going to be degree 4, which is even. And the leading coefficient is 1. So that's positive. So the end behavior will be the end behavior of a even positive leading coefficient, which will be up in both directions. So we can write as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x also approaches infinity. Now, before we can do the zero chart on this one, there's going to need to be some factoring. I think we can do the scratch work right here, but you may need, depending on how large you write, you may want to go to a separate piece of paper and do the scratch work factoring. Looks like everything has a common factor of x squared. So we can write this as x squared, and then it'll be x squared minus 4. That can factor one more time into x squared, x plus 2, x minus 2. So it's that difference of squares factoring pattern that you should always be on the lookout for. So then we have a 0 at x equals 0, a 0 at x equals minus 2, and a 0 at x equals plus 2. Remember that the zeros are like the opposite of the sign in the factor. Just like with quadratics and everything else, it kind of behaves that way. So to make the zero chart, we can say, what is a 0? What's the multiplicity? And what's the behavior? What does it do? Let's do ZMB. Negative 2, 0, and 2 are the zeros. The multiplicity, well, the 0 at x equals 0 had a squared, so that's going to be multiplicity 2, and the other 2 just had a power of 1. So those are going to be multiplicity of 1 each. So we have 1, 2, and 1. The 1s will cross, and at 2, it bounces, which you could also say is touch and turn around. That should be all you need to make the graph. So go ahead and plot the zeros, negative 2, 0, and 2. The end behavior is up and up. I'll just do little arrows on here to remind me, although I'll probably erase them later. So if I have to cross, bounce, cross, they'll have to be coming in from the top, cross, turn around, bounce, turn around, and this one probably is pretty symmetric, and then cross back up again. It kind of looks like a nice W. That's a pretty cool shape. So let me clear off the pencil marks and clear off some of these extra marks and like kind of lock that in. So we're going to cross, turn around, bounce, turn around, cross again, go up to positive and negative infinity. My arrows aren't the same length. That's okay. We have our 3 zeros again with their different behavior. That's our example 3. Let's go to example 4. We looked at this one already also. We said the degree was 3 because it's next to the third. And in this case, that was important that 3 was odd. And the leading coefficient was -1. So this is going to have the odd negative behavior. Odd negative is maybe the hard one to remember. It's going to go up to the left and down to the right. So as x approaches infinity, f of x will go down to negative infinity. As x approaches negative infinity to the left, y or f of x will go up to infinity. So that's our end behavior. Now to make the zero chart, we need to factor this. So I'll say factor. And I know that there's not enough room here to factor this, so we're going to go to some scratch work and factor this down below. So I said I wasn't going to talk a lot about factoring, but sometimes if you want to do a polynomial, you've got to factor it out. This one is lucky. We only have 4 terms and a power of 3, so this shouldn't be too terrible. First thing, I see all those negatives, and I'm just kind of saying no thank you, so I'm going to say, all right, let's call f of x -1, and then times the positive version, so x cubed plus 2x squared minus 4x minus 8. I want to remember that -1 and then kind of ignore it for the rest of this procedure. So we'll say -1 times. Now I'm going to do this. It's 4 terms. The best move here is to do this by grouping. So we can group the x cubed plus 2x squared together. And I'm going to regroup such that the minus 4x minus 8 is in its own set of parens. When we did grouping before, we mentioned this. This is really important when your third term is negative here. Make sure you put that in the parens and make a plus that separates the terms, or it's not going to work out quite right. Let me copy my -1 down. Now we're going to look for a greatest common factor in each of the terms. So x cubed and 2x squared seems like it has a greatest common factor of x squared, leaving an x squared x plus 2. And the second term here, so we'll do plus. Here I have a greatest common factor of -4. So notice that because I have the negative, everything kind of came out negative. -4x over -4 is x, and -8 over -4 is plus 2. Now we're grouping. That is a common factor in each term. So we can factor one more stage. -1. X plus 2, that was the common factor. I'll pull it out to the right and have x squared minus 4. So -1, x plus 2, x squared minus 4. We are not done. We are not done. X squared minus 4, we saw in the last problem, is a difference of squares. So that's x plus 2, x minus 2. We also have this -1 and an x plus 2 from earlier. So then altogether, we should have -1, x plus 2 squared, x minus 2. That's going to be the fully factored version that we need to work in. And notice how fully factoring this sort of like changed the multiplicities, not changed them, but like revealed the multiplicities of the zeros. All right. So let's copy that in. So it was -1, x plus 2 squared, x minus 2, I believe. So we have a 0 of -2, and we have a 0 of 2. And if we make our chart, so the 0, the multiplicity, and the behavior, there's only 2 zeros on here. So at -2, we had a multiplicity of 2, and so the behavior is going to be a bounce. That multiplicity of 2 is because there's an exponent of 2. At positive 2, there's a multiplicity of 1, because it's just an exponent of 1, and that's going to cross. All right, so we have a 0 chart, we have our end behavior. Let's make the graph. -2, 2. Ends should look like this. We have to, we'll sketch it in again, we kind of have to come in, we have to bounce, we have to turn around, we have to cross, so it's got to look something like this. And then as I plot in with my pen, I'm going to follow that, come in, bounce, turn around, hit that 0, cross straight through, and come on out. I'm not very happy with that, so I'm going to resketch it. I'm going to try to do this last one really, really good. Come in, bounce, cross. Ah, it's too linear. I'm trying to make sure they look like good, smooth curves. Okay, that's going to have to be good enough. It should probably be a little curvier, but that's okay. 2 zeros, bounce, cross, bounce, correct end behavior. That's all you need. All right, so we have graphed a number of polynomials. Just to recap, if you needed any, we'll freeze frame. Here's the first 2. And here's the second 2. You can pause the video if you need to freeze frame and see more. And at this point, that is all you need to graph polynomials. You have your end behavior test, your leading coefficient test for end behavior, you know about zeros and their multiplicities, and you can plot all of those things on a graph with one smooth curve. Now, if you're happy with that, leave, go, do your homework, you're done. But some people always ask me, Mr. Eck, why? Why does this stuff happen? Why are these tests the way they are? So, if you're curious, stick with me for maybe 10 to 20 more minutes. We'll call this just the end half of the video, and I want to talk about why those tests work. So, again, why does that leading coefficient test tell us the end behavior? And this is definitely bonus content. You only need to stick around if you're curious, but if you are, we'll try to talk about it. So why does the leading coefficient test tell us the end behavior? I broke that up into three different questions. First, why does only the first term matter? Second, why does the degree matter, or what does the degree do? And third, what does the sign do? Because those are the 3 parts of the test. So the idea of the first term mattering is, let's just think about orders of magnitude. Let's think about an x to the third minus x squared, right? Just like, let's call that f of x. Now, what if x is, let's just, like, x is 10, right? What if x is 10? I don't think I really need a calculator for this, but we can play, right? 10 to the third is 1,000. 10 to the 2 is only 100. So when I do, if x is 10, then f of 10 is 1,000 minus 100, which is still 900. And the idea is that this exponent, even when x is 10, which is not very big, that exponent is taking like an additional power of that big number. That term is just going to be completely in control. It doesn't really matter that I'm subtracting 100 when I have, forgot a 0, when I have 1,000. What if I do, let's just do like one more power. What if x is 100? So 100 to the third is this. 100 squared is that. And if I just try to do that, is that 1,000,000 minus 10,000? It's not going to have a significant difference. The x squared term contributes essentially nothing to the total when x is large. And that's true no matter, right, these degrees were only different by 1. If that exponent was even bigger, you know, an x to the 7th or an x to the 4th, that would take over even more. So, but even an exponent that's different by just one difference means that that term, like, basically controls the size of the total y value, because the just exponents have so much power and weight here. Okay, So why does the degree matter? Like, we said, all right, x to the third is in charge. Why does the degree matter? Well, let's just think about y equals x squared versus y equals x cubed. What does x squared look like? It's a parabola. And specifically, it's a parabola that goes up and up. Because if you have a positive number squared, you get a positive. And if you have a negative number squared, you get a positive. It's very boring. So that means you're going to go up and up on both sides. And since the first term is the only thing that matters, x squared, or anything even, is going to give you positives on both sides. On the other hand, let's think about y equals x cubed. What does that look like? Well, it's one of our important parent functions, and it looks like this. And if you have a positive number, and you cube it, whatever it is, you're going to get another positive. But if you have a negative number, and you cube it, you're going to be multiplying it by itself 3 times, that's going to give you another negative number. Which is why, to the left, the graphs of cubics go down. Well, if the leading degree is the only term that really matters, and we have any kind of odd exponent here, it's going to share the same behavior with an x cubed, that when you have that negative x and you take it to an odd power, it's going to stay negative, just get more and more negative, pulling the graph further and further down. And why does the sign of the leading coefficient matter? Well, just ask yourself, why does x squared go up, but negative x squared go down? This looks like this, but this one looks like that. The negative is just a reflection over the x-axis. And that's all the negative thing does. I wrote question 4, does this test work for non-polynomials? Nope. Basically, polynomials are so regular, each term has the same structure. There's no different number thing going on with different terms, and you can almost always factor them to find the zeros. This leading coefficient test only really applies to polynomials. Other graphs, e to the x, rational functions, all bets are off. They have their own separate tests. So this is really just for polynomials, by the way. Okay. So the second set of questions was, why do the graphs cross, flatten, or bounce at the different multiplicities of zeros? Why does that happen? And I kind of broke that into 2 separate questions too. So the first question is, why does x plus 2 squared bounce at x equals minus 2? Well, we know that this graph, without any other polynomial stuff, would just be a parabola shifted to the left 2 units and do this. But let's think about what's happening with the table of values for that graph. So I went to my calculator and I plugged it in, y equals x plus 2 squared. And I just, instead of looking at the graph, which I already know, I looked at the table. And scrolling over to negative 2, you can see the 0. But just look at what happens as I go by 0.1s approaching that, right? As I go, so I'll start at maybe negative 1. I got 0.49, 0.36, 0.25. I'm squaring numbers that are smaller than 1, so I'm approaching 0, getting smaller and smaller. But because I'm squaring those numbers, when I hit 0, I don't change sign. I stay positive. So it curves in towards 0, but then it doesn't change sign because it's a squared. Powers of 2 don't change sign. So it has to bounce, because if it crossed like that, we'd be going from negative to positive for the y's. But we don't. Just look at the table. So that's why there's a bounce there. So what about the second question? Why does x minus 1 to the third flatten out at x equals 1? Well, I wanted to go again to the calculator, and I'm actually going to ask a sub-question. Maybe we should be asking, why does x minus 1 to the first not bounce, not flatten? Well, x minus 1 to the first, if I graph it in, and I didn't need to write that 1, but I put it there for structure. The graph here is just a straight line going through 1. So then if I look at the table of values and I scroll down to 1, Notice as I approach 1, I'm just increasing linearly. The y values are going up at the same rate the x values are going up. There's the 0, and then it switches signs, so it's going to cross from negative to positive, but it's not going to flatten out because the approach is linear. But what if I change this exponent to 3? Then the graph looks like this. It's a cubic, and it should cross 1, but notice how the cubic part flattens out. And if you look at the table, you notice, let's scroll from 0 again, because at 0 we have 1, and then we start getting fractions, but we're taking exponents of fractions, so the numbers are getting smaller, but not at a constant rate. The numbers are getting smaller faster as you get closer to that 0. 0.64, 0.27, 0.008, 0.001, 0. And these are all negatives because they're to the left of that 0, but then as you go to the right of that 0, you get the same symmetric values, but increasing again. So the third power flattens out because you're taking an exponent of numbers close to 0, just looking at the chart compared to the linear chart. So that's why we have this flattening behavior. Now, if you combine these two, basically each of these near 0 behaves like near that factor behaves like that factor. So if I were to graph this polynomial, just as a quick sketch, at -2, we would bounce. Now this would be odd, so it would be will be accurate, right? This would have degree 5, so it would have to do this and positive coefficient. So at -2, it's going to have to come in and like bounce and not change sign here because x plus 2 squared doesn't change sign. But then at 1, we have to come around and kind of behave like the cubic part. We have to come around and flatten because the cubic part flattens. And because that cubic part flattens, the other part doesn't matter. So when you're looking at the factored form, this part is the x plus 2 squared, and this part is the x minus 1 to the third. And it's kind of like a weird hybrid of the two graphs of those individual polynomials, and maybe with some reflections because of the end behavior and the signs and stuff. So that's how that graph would look, and why it would flatten and bounce in those ways. It's really just about the signs and taking powers of fractions. And just to close on this idea and kind of close the video out to what we've been talking about, why do both tests work? Polynomial graphs behave globally, end behavior on a large scale, like the highest power term if it was graphed alone. That, you know, x to the fourth is going to, plus a bunch of garbage, is going to behave like x to the fourth. X to the seventh is going to behave, plus a bunch of stuff is going to behave like x to the seventh when you zoom way out. On the other hand, when you zoom way in at a specific 0, then the graph will behave like the factor that gave that 0. So you have a square factor, you're going to bounce because x squared bounces. You have a cube factor, it's going to wiggle because x cubed wiggles. You have a first power factor, it's going to go straight through because that's what lines do. And then it's kind of this weird, to make the total graph, is this weird mishmash of the end behavior on the left and right, and the zeros on the others, and the zeros in the middle. And that makes the total polynomial graph. So that's kind of the closing idea of the graph. And as you graph more and more of those, you'll get a really good sense of it. All right, everyone. Well, thank you for sticking around for the bonus content. That's been super fun to explain. I hope it was helpful if you're wondering why the tests work. Good luck with graphing these. Go make sure you have all this page in your notes. Make sure you have these tests on lockdown. And I will see you all in class. Thanks for watching.